Welcome to another LEAP seminar. Today we have the pleasure to have Nuno Barros. Nuno has been around in LEAP, with us in LEAP for a long time. He did his master's degree in school, in Faculdade de Ciências, followed by 2 years at CERN in the computation group of Atlas as responsible for the implementation of the conditions database. Then he did his PhD at LEAP and Faculdade de Ciências within the SNOW experiment on the optical calibration and analysis of solar reactor Neutrino Oscillations. He did his first postdoc in Dresden, now in the SNOW Plus and Gerda experiments. In Gerda, he was responsible for the phase 1 analysis and the group of liquid argon instrumentation. In SNOW Plus, he covered various leading roles like Monte Carlo software, solar neutrino analysis, reconstruction. He is currently the water phase analysis coordination and optics calibration coordinator. His second postdoc was at Penn University working on SNOW Plus and DUNE. His responsibilities there were the implementation of the electronic trigger in DUNE's 35 tons and the ProtoDUNE single phase, and is also the deputy run coordinator of DUNE 25 ton. He has been with us since a few years. He won one of these researcher positions by FCT, and today is going to give us an overview of the DUNE experiment. Thank you, Nuno, for being here. Please start whenever you want.
Well, thank you for the invitation for the seminar. So I'll be talking about the DUNE experiment. And so what are our goals, what is the status, and what can we hope to achieve. So this is the outline of my talk. I'll introduce a little bit the neutrinos, because I understand not everyone is familiar with all the motivations. I'll talk about the motivation for DUNE in terms of neutrino physics. Then I'll introduce the experiment. I'll talk a bit about calibrations, which is also happens to be one of the main activities that we carry out at LIP. And then I'll talk about the prototyping and what is its status. So introducing a little bit the history of neutrinos, and neutrinos are a bit of a desperate hypothesis, and it came out as a solution to a problem for the beta decay. And Pauli admitted when he proposed that solution that he was doing something very bad, because he postulated that neutrinos would not be possible to be detected. Of course, nowadays we know that that is not quite true. And so since the postulation by Pauli, we do have quite a bit of an history about neutrinos. So in the 30s, the neutrino, Pauli proposed the neutrino to solve the problem of the beta decay, and 26 years later, we actually managed to detect neutrinos by Fred Rines. And then since then, we discovered that neutrinos have this kind of habit of every time that we get an answer from them, we get also a bunch of questions. And so we detected neutrinos, and then we figured out that there was an issue with neutrinos coming from the sun. Later on, we already saw neutrinos from supernova. We saw neutrinos from basically atmospheric neutrinos. And along with that, we got one of the answers about neutrinos is that they oscillate. And that actually, later on in another experiment, we gave us the solution. We figured out that that was the solution for the problem that was postulated in '68. So neutrinos come from a wide range of sources, and that comes from the Big Bang all the way to extragalactic. And so you can see that the range of energies that we can get them is just enormous. We are talking about 20 orders of magnitude over here. And in this talk, I'll be focusing on something around the accelerator neutrinos, so some neutrinos about the GeV energy range. So what do we know about neutrinos? We know that they are the only elementary neutrofermions. So that means that since they have no charge, they do not participate in electromagnetism. And this opens the possibility for an interesting fact is that they could be their own antiparticles. They come in three flavors that are listed here: electron, muon, and tau, which basically pair with the corresponding charged leptons. They are very light, so light that they were thought to be massless for many, many years, although by the discovery of neutrino oscillations implies that they do have a mass. And we know that they interact very weakly. They are really only subject to the weak interaction. So the neutrino mass, it's an interesting parameter that is worth taking a look, is because neutrinos are massless in the standard model. However, oscillations imply that they have mass, but measuring this mass is not quite an easy thing to do, because since they are neutral, they don't curve on an electromagnetic field, they don't decay because they are extremely light. And so we have to look for them through an effect of quantum interference. There are, of course, quite some interesting questions about them. Is that, for example, why are they so much lighter than pretty much all the other fermions? And that is a question that it's worth keeping in mind, because we'll come back to it a bit later. So I just mentioned a moment ago that neutrinos come in three flavors. And so those flavors basically correspond to the lepton that is produced on the charge current interaction. What happens is that neutrinos also come in three masses, but these mass states are not the same as the flavor states. And so if these masses are non-zero, and the flavors are basically combinations of the mass states, this means that the flavor can change. And so that is basically the principle of neutrino oscillations, in which we have weak flavor eigenstates and we have mass eigenstates. And so since the weak states are mixture of the mass states, this means that we can have actually energy and time / distance oscillation probability. And in a case of a two flavor, that is basically explained through this equation. And here it's interesting to note that there's two pairs of parameters that are worth looking at. Is that we have a mixing angle and a mass square difference, and those we can call them as fundamental oscillation parameters that are really tied to the physics. And then we have an L and an E, so a distance and a neutrino energy, and those are experimental parameters. And this basically guides us on, depending on the physics that we want to do, guide us on how do we decide the experiment, how we basically build the experiment to do the physics. And so how do we build an experiment that looks for neutrino oscillations? Well, we choose the L and E that is adequate to the ranges of delta M squared that we are interested in. Of course, then we need to get also a suitable neutrino source, and then we collect a lot of data to see neutrinos appearing through oscillations or disappearing with respect to the ones that we produced. Because this, so in the bottom plot here, we are basically representing how the flavor content is changing with respect with the distance. And this, I believe it's for a neutrino energy of 1 GeV or so. So in fact, neutrinos, this was just explanation at two flavors, but we do have three flavors. And so in three flavors, the algebra is pretty much the same, except more complicated. And so we have a matrix. So basically the neutrinos become parameterized by three masses, three mass states, and three angles, and an extra complex phase. So this is known as the PMNS matrix, which is basically the neutrino equivalent of the CKM matrix that we see on the quarks. And this delta phase, this complex phase, is actually responsible for the CP violation, which basically is telling us whether neutrinos behave in the same way as antineutrinos. So a difference between matter and antimatter. And so this brings us that we have already that neutrino oscillations already has incorporated a possibility that they might behave differently. So in the last 20 years, of course, oscillations were thoroughly tested, and we got different kinds of experiments that are sensitive to different parameters of the oscillation matrix, gives us a pretty good picture of what we got. So we got accelerator and atmospheric neutrinos giving us the 2-3 sector of the matrix, the short baseline reactor experiments like Diabay giving us the 1-3, and then long baseline like Camland, and the solar neutrino experiments giving us the 1-2 sector. So this summarized what we know, but as I mentioned, every time we get an answer about neutrinos, we get 5 questions coming with it. And so what do we still want to know? Well, one is there CP violation in the lepton sector? This is a very important question because it is pretty much the only parameter that is not fully known out of this matrix. The others are, we have pretty much nailed them down with more or less uncertainty. Another question that is interesting is that we do know we have 3 mass states, but we do not yet know the exact ordering of those mass states. We know that nu2 is higher than nu1, but we don't know whether nu3 is above or below. And that is basically what we call the hierarchy. We still don't know whether neutrinos have normal or inverted hierarchy. And of course, we also would like to know what are exactly precise values of the mixing parameters, because that also leads us to try to understand why the PMNS matrix is so much different from the CKM matrix. Of course, there's other questions, like, for example, what is the absolute mass scale? Because we know the square differences, but we don't know the total scale here. And for example, whether neutrinos can be their own antiparticles. This and the DUNE experiment, which I'm talking about today, is actually aiming to answer most of these questions, except for this one, which is another experiment that LIP participates on that is trying to answer. And so this basically brings us the summary about neutrinos. And now one thing that I brushed very early on was about the matter-antimatter asymmetry. And this is interesting because our universe, as we see it, is matter. But our physics tells us that we should be producing antimatter. However, and so it's interesting to try to understand where is this asymmetry coming from. And so talking about matter-antimatter asymmetry brings us to talk about baryon asymmetry and the Sakharov conditions that basically postulate how can we produce baryon asymmetry. And so we do need, there's 3 conditions, processes that violate baryon and lepton number conservation, and well, there should exist such processes in the standard model. The departure from thermal equilibrium, which we can assume that in the extreme conditions of the early universe, we can obtain these conditions, but we also need some difference between matter and antimatter. And this brings us, well, we just talked about CP violation. Now, is this enough? Well, CP violation has been observed in K and B mesons, but the amount that was observed is not enough to explain the asymmetry. However, the PMNS matrix has a CP violation phase, so CP violation could exist in neutrinos, and maybe it could be enough through basically a process of leptogenesis, which leads to a process of baryogenesis. Of course, this is only one piece of the puzzle. Another piece of the puzzle is that neutrinos, if they are their own antiparticles, that means it's basically the difference whether they are Dirac or Majorana particles. So in the case of neutrinos, unlike the other fermions, neutrinos are neutral. So it's not obvious whether neutrinos are or not their own antiparticles. They could be their own antiparticles and having just the chirality, making the distinction. Now, the question is is the characteristicity a fundamental property of the neutrinos? And that's an interesting question on its own. And these two pieces, if we actually combine them, we can actually give us that if neutrinos are Majorana fermions and they do violate CP violation, we could, through a process, basically, or the process of leptogenesis, do explain the matter-antimatter asymmetry in the universe. So if neutrinos, could be their own antiparticles, we could, for example, assume if there is a heavy Majorana neutrino, that could help us explain the small masses of the neutrinos that we see, the active neutrinos that we see in our nowadays, in our time. And an interesting thing is that if we assume, we go look at the Dirac term, and we assume the gut scale, we could get, assuming the mass of the heavy neutrino on the gut scale, we would get our light neutrinos to have the mass that we are more or less expecting from our oscillation limits. This is quite an interesting thing. And this basically means that if we see, by looking for the CP violation, we are indeed actually looking also, if we are at least probing, taking steps towards looking for the matter-antimatter asymmetry as well. And so this is one of the many motivations of the DUNE experiment. And so now let's go see a bit about the experiment on its own. So the DUNE is a very large collaboration. I believe, yes, that right now is the largest neutrino physics collaboration. So we have over 1,000 collaborators, almost 200 institutions, 34 countries, including plus CERN, because, well, CERN is its own thing. And you can see on the map that is really a quite global collaboration. This picture is from the last collaboration meeting before confinement came in. So, and you can see it's already a pretty sizable, and still this is only a small portion of the collaboration. So the DUNE experiment is basically will have it's an accelerator based long baseline experiment on its base. So the neutrinos will be produced at Fermi Lab, in Illinois, close to Chicago, and they will be detected in SURF in South Dakota. So we'll have about a baseline of 1,300 kilometers. So this will be the source, and basically we have the booster, and I'll show in a moment a bit how the neutrinos go. And this is basically the surface at SURF where the DUNE detector will be located. So we can split the experiment into several sections. And so for the moment, let's start by looking at the far site. So the far site, as I mentioned, is at Sanford. This is basically a gold mine that was repurposed into an underground laboratory. The laboratory is about 1.5 kilometers underground. There are already experiments there. There are two main campuses, the Davis campus, and that's where we have already several experiments where historically the Homestake experiment, the first one to see solar neutrinos, was located. There's Lux and LZ, now LZ, are located there. There's also Majorana, that is a double beta decay experiment there. And then there is the Ross campus. This is the Ross campus, and this is where DUNE is going to be located. And so, oh, sorry, I did actually say the name in reverse. And so this is what exists underground underneath these two shafts. And so the Ross campus is where DUNE will be located. And basically we'll have 3 halls, which basically means 5 cavities. And I will explain a little bit more over this. And those cavities have already been ground was broken into 17, and now they are in the wall cavity itself is being excavated. So the far side will have 5 main caverns. 4 are for detectors, for 4 different cryostats, and 1 support cavern. The support cavern will basically have cryogenics and the DAQ, basically the instrumentation, and the other 4 will basically be occupied pretty much by the cryostats. The detectors are designed to be based on Liquid Argon TPC technologies, to all of them to use essentially the same cryostat. The cryostats themselves will hold basically 17 kilotons of liquid argon, out of which 10 will be fiducial. That's pretty much, and so by combining the 4 cryostats, we'll finish with 40,000 tons of liquid argon fiducial mass. So the detectors will be built in a staged approach. So we'll work on the first one, start taking data, and then move on. And then while taking data with that one, we'll be building the subsequent ones, which might or might not use the same technology. So in the end, there is no guarantee that they will all have the same technology. Actually, on the contrary, there's almost guaranteed that they won't all have the same technology. And this will allow to actually improve the technology, add improvements as we build the full experiment. So moving on to the detectors themselves, the detectors, as I mentioned, they are liquid argon TPCs. They will be, liquid argon is both the target and the detection medium. And we plan that we will in principle have different detector designs on the different cryostats. So right now there are both horizontal and vertical drift designs. And horizontal vertical drift, that means how the field, the direction of the field, and therefore the direction that the electrons will drift. In this talk, I'll focus on the horizontal drift, which is the one that has been around for longer. And this is technology that is confirmed for the very first module. The cryostats will also have a photon detection system. Well, the detector will have a photon detection system, which will, of course, will help for the reconstruction and will provide T0, in particular for non-accelerator physics. And as I mentioned, the models certainly will not be identical. And the idea is really that we can add improvements as the detector is building along. So about the liquid argon TPC, so this is a technology that has been around for quite a while. It has been used with Icarus, Argonaut, Microboot, Lariat, but not quite on the same scale that DUNE is using. So in DUNE, we'll have at least 2 modules to use this technology. The first one guaranteed. This is a technology that gives no signal amplification. On the other hand, we will be able to see both the ionization electrons and the scintillation photons. And so in this figure, we can actually see a bit how the liquid argon TPC works. And you can see a track leaves, there is ionization produced, and then the electrons drift to the anode wire planes, and we continuously record and get the projections of the tracks that were produced. So we are essentially taking a continuous picture of what is happening inside the active volume. The technology this technology has quite a lot of advantages. One of them, well, argon is cheap. It's not such a big issue to get a very large volume of argon. It has good dielectric properties, so that means that we can put a very high voltage to produce a drift that is, well, for long drift ranges. We can do 3D imaging, so this is basically it's important for the reconstruction of the events that we see, and we basically get full event topology because we don't have an inherent threshold, energy threshold for the physics, like for example on Cherenkov. Of course, there's also some major challenges, like every technology that seems really, really good, is that, well, the event reconstruction is quite a challenge because we have a monolithic detector. And so everything shows up, as you can see in the picture on the right, everything shows up there. And now we have to be able to identify everything that is here. And so the scaling of technology is also in itself a challenge. And so, for example, one of them being the high voltage. As we make the detectors bigger and bigger, we need to be very careful with readout, noise, high voltage, and all that goes with it. So, however, that's what we are working on. And so in the case of the single phase liquid argon TPC, for DUNE, we'll basically have alternating anode and cathode planes. This will have, on this first module, we'll have basically a drift distance of 3.5 meters with an electric field of 500 volts per centimeter. So this basically tells you already what is that we are basically having a cathode voltage of 180 kilovolts. So this is not a small amount. And therefore you can see already quite some challenges that arise from this. We have 105 anode planes. These are our readout modules, and you can see a picture of one such plane on the bottom. So this basically accounts for about 380,000 channels, and we are basically digitizing for several milliseconds. So we are not, the triggering in DUNE is done post-processing. So we digitize continuously, and then we decide what we keep on the triggering. And basically, we are continuous digitizing the waveforms. So this is a slow technology. So I will skip a bit of this. And one part that is important to notice here is that these anode planes, in order also to cut on the number of channels, they actually have 3 readout planes on their own that they are placed on different angles. And basically there are 2 induction planes and 1 collection plane. And the fact that they are put at different angles allows us to triangulate to perform the 3D reconstruction. And so this is pretty much how a signal is formed in the TPC. And so these first 2 layers are the induction planes, and they produce bipolar signals as an electron drifts by. And then we have a collection plane, and this is what ultimately gives us the energy. So ultimately, these 3 planes allow us to get energy from the collection and 3D positioning from the induction, because the shape of this bipolar signal is going to depend from the direction where the electrons are drifting from. So as I mentioned, there is also a photon detection system. So right now, the system originally was based on plastic scintillators. Nowadays, we are assuming a better alternative has been shown up. This is a work performed largely by our Brazilian colleagues, and it's called Arapuca. And this is basically a very nice method that uses dichroic filters that allows us to actually separate basically the light. Okay, that allows us to actually detect light in different ways. So they build pretty much photon traps. And then ultimately the light is collected by silicon PMs. In principle, the DUNE 1 cryostat is going to have about 6,000 of these cells that will allow us to see the photons, the scintillation photons. And with this, that's how we are going to trigger, for example, on non-beam events and allow us to get T0. So now moving on for the accelerator itself, and near site. So as I mentioned, the beam is going to be produced at Fermilab. This basically, it comes out of, well, we have basically the booster, the main injector, and this is the new beam line that is going to be built for DUNE, pointing towards South Dakota. And so in fact, if looking in profile, what we'll have is that we will have actually a hill of about 20 meters so that we can curve the beam pointing downwards, because the beam has to point about 5.8 degrees downwards so that it passes by the DUNE location in South Dakota. And so the beam is going to will have a 1.2 megawatts proton beam with a wide range of, so basically with 6 to 120 GeV protons. So there are plans to later on upgrade this beam to 2.4 megawatts, which would allow us to get substantially more statistics. And basically on the baseline, we'll have about 10 to the 21 protons on target per year. So the beam itself uses a horn, and it will have basically, it will be on axis and a wide band. So this is basically the estimated neutrino energy of the muon neutrino energy that we'll expect. And the reason for being wideband is that we would like to see both the first and the second oscillation maxima, because that gives us extra handles for the oscillation physics. Of course, the horn itself will be, the polarity will be selectable, which means that we can do both neutrino and antineutrino modes. And so this means that we will have both neutrino, electron neutrino appearance, muon neutrino disappearance, and the anti-version as well. So we'll have essentially 4 spectra to analyze. So after the accelerator, we will have a near detector. And basically the main objective of the near detector is, well, one is to constrain the flux and the cross-section systematic uncertainties. And of course, we can measure interactions and do physics out of that as well. And so right now, the concept for the near detector in DUNE is actually a 3, is not 1 near detector, it's 3 near detectors. There's a pixelated liquid argon TPC, codenamed Argon Cube. That's the name of the prototype going on right now that has been carried by Berkeley and Bern. And then there is a multi-purpose detector, basically with a magnet, an ecal, so that is represented down here. There is a TPC, an ecal, and then there is a beam monitor that is basically using 3D scintillation tracker, 3D scintillation tracker spectrometer. Now, one interesting thing about the near detector is that 2 of these are actually expected to be movable. And that's what is called DUNE prism. And so both the Argon Cube and the multipurpose detector are on rails. And the idea is to move it so that we can do near off-axis detection. And that's interesting because we can do about 30 meter side movement as represented here, and this allows us to deconvolve flux and cross-section. And so basically each position that we move to the side is basically giving us a whole new flux measurement. And so this means that, as you can see here, we start getting, we start getting a new flux measurement on a narrower energy range. And so this allows us to deconvolve and therefore further constrain our systematics. And so, and finally, about the physics of DUNE. So DUNE has a pretty broad range of physics. So it's ranging from neutrino oscillation physics, and that's our primary physics program. We aim for high sensitivity potential for the leptonic, for search for leptonic CP violation. We want to identify, and this is something that comes almost for free, the neutrino mass hierarchy. And of course, since we are doing such a big experiment, we want to measure the oscillation parameters with as much precision as we can. We also have other physics on our program, like proton decay, and the fact that we use argon, this actually allows us to look for SUSY favored decays with kaon modes. And those are interesting because DUNE is particularly sensitive to these because we do not have a threshold to see the intermediate states. Of course, we'll be active and looking for supernova bursts. This basically, we have a unique, since we have argon, we have a unique sensitivity to electron neutrinos, which differs from most other detectors that are based on inverse beta decay, and therefore they are sensitive mostly to anti-neutrinos. And the design of DUNE is basically to be sensitive up to the satellite galaxies. Of course, we want to do atmospheric neutrino analysis and with the near detector as much neutrino interaction physics as we can. And this whole program actually ranges from a few MeV all the way to a few GeV. So it is a really broad program, not only in topics, but in energy as well. So the long baseline physics, this is the staple program. So this is, in a nutshell, we will basically be producing a muon neutrino beam, fire it away towards Sanford, and in Sanford we detect both muon neutrinos and electron neutrinos. So the baseline is 1300 kilometers. The energies are ranging quite a bit. So in the range, basically 1, 2, 3, 4 GeV. And then at SURF, we'll be measuring basically muon and electron neutrinos, and this will allow us to probe for neutrino oscillations. The baseline is sufficiently long where matter effects actually do matter. And so they are relevant for us. And then, of course, we plan to do this, repeat all of this with the antineutrinos. And the fact that we do neutrinos and antineutrinos allows us to do a direct probe of the CP violation on the neutrino sector. And so, in fact, as I mentioned before, we will have ultimately 4 spectra. We'll be looking for muon or anti-muon neutrino disappearance, and we'll be looking for electron neutrino or anti-electron neutrino appearance. And through these 4, we can basically look for the mass hierarchy, delta CP, and be sensitive in particular to the θ2-3 octant, and test the 3 flavor paradigm. As I mentioned, the baseline being very long, matter effects are quite large, and the fact that we can look for the disappearance and appearance of over a wide range of energies has an additional benefit, that is, we can disentangle the mass hierarchy effects from the delta CP. And this is basically the rationale, is that the mass looking for the mass hierarchy and the delta CP, they do both yield a similar effect into the transition, into the oscillation probability. They both basically change the height of the transition peak. So in principle, they would be degenerate. What happens is that these 2 effects actually depend differently on the ratio of L/E. And so by looking at the shape of the full spectrum and using a broad spectrum, we can disentangle them. As you can see here, the effect of the CP phase not only changes the height, but it's different with the baseline and neutrino energy, while the mass hierarchy has a slightly different dependency. And so this allows us to disentangle the 2 effects and be both sensitive, competitively sensitive to the mass hierarchy and to the delta CP violation. And so in terms of the sensitivities, we in principle can have a mass ordering nailed down within 2 years at a 5 sigma level, once we have beam data. And for the delta CP, we can pretty much cover about 75% of the range for delta CP at 5 sigma level after 15 years once beam starts. And this is already considering that we are running staged. And so that's also why you see that the effects here, these lines are basically undulating. So other physics that we are sensitive for, liquid argon detectors. So we plan to do, we have quite a program for looking for nucleon decay. We are sensitive to several decay modes: proton, neutron, and bar oscillation. One of the advantages that, as I mentioned, we don't have, for example, a Cherenkov threshold. And this means that we can look for modes that usually would be difficult to see because they would pass, some final state particles will not be visible, namely kaon modes. There are many channels that will be searched for. Phenomenology is extremely rich. There's over 90 modes that have been identified. And one thing is that using the imaging and the kinematics in liquid argon actually allows us to have almost linear sensitivity with exposure. And this is quite good because this is an experiment that's going to run for a very long time. We also plan to be supernova sensitive. This means we are going to look for charge current interaction on argon-40, which is rather unique for neutrino detectors that are running nowadays. And this actually gives a sensitivity to the mass hierarchy. And besides that, we can also even see the peak of neutronization, which corresponds to a burst of electroneutrinos that is produced when the core, with the core neutronization burst. And this is basically what I'm representing here. So with no oscillations, of course, we would have a gigantic peak here. But depending on the ordering of neutrino masses, we might, whether we see a peak or not, that actually tells us the mass ordering. And so this is a very exciting prospect to, if there is a supernova, we can actually do quite a lot of physics with it. And of course, we also are sensitive in principle to low energy neutrinos, namely, for example, solar neutrinos. And the interesting part for doing solar neutrinos here, so it will be hard to go to very low energies, but we will be able to detect through both charge and neutral current. And the interesting part here is that each of them will have a signature that will allow us to look specifically for these events. So we could in principle separate the different channels by looking at the associated photons that that come with each channel. Now, the interesting one part here that comes interesting is that this gives us the possibility to look for the one missing neutrino flux to be measured. And that is the HEP solar neutrino flux. And since that is the highest energy of the solar neutrinos, and by using the charge current, we can actually quite disentangle from the boronate, which we could not, and well, of course, factoring in also the size of DUNE, that is a much larger detector than most other neutrino detectors looking for charge current. That was basically the last one being SNO. And it was SNO that has the current best limit for this flux. So we are quite hopeful that we can also do some solar neutrino physics with DUNE. So, of course, all of this physics is very interesting, but we need to know very well how the detector looks like and how the detector behaves. And that's where calibrations come in. And so basically it's how can we make and get the best physics out of our detector? And so the reason for calibrating is, well, is because the systematics are really a substantial part of the energy systematics are really a dominant systematic for many of the physics that we want to do. Of course, flux, cross sections, they have their own large contribution, but for example, for the delta CP, you can see clearly that energy scale and energy resolution are by far the dominant elements. And these, to reduce these the way to go is really to calibrate. So DUNE has quite a lot of calibrations that relies on. So of course, including external measurements, there's some sources that can be used, intrinsic sources like muons and, well, other intrinsic, for example, argon 39. But we also plan to have some instrumentation installed and some dedicated external calibration systems. And I highlight two of these because these are the ones that we are involved in LIP. And so of the external calibration systems, the most, let's call it the most relevant ones here would be the ionization laser. And this will, with this, we plan to measure the electric field, to basically map the electric field and possibly even measure the electron lifetime. Then there is a pulse neutron source, and this is basically to look for homogeneity of the detector. It's basically a source, it's a neutron source, and we look for the neutron captures within the detector. Then there is a plan also for a radioactive source using basically a californium nickel source. And then there is other calibration systems, mostly aimed for the instrumentation. So I'll talk a little bit about these two in principle. So the ionization laser, that's something that we are quite involved here at LIP, and basically we use a high power laser and then going through a mirror system that allows us, that we can move, that allows us to basically create a steerable beam within the cryostat. So this is a technology that has already been shown, it has been deployed in microBOON. Of course, now we are talking about something that is substantially larger in a whole new cryostat. And so the major goals for the laser system is to map the electric field distortions and the drift within the drift volume, hopefully within 1%. And if we can do a secondary measurement of the electron lifetime as well. So this, as I mentioned, has already been shown. It has been, for example, these are the results, the electric field distortion of within the microBOON experiment. There has been, you can see here, basically an event of basically the beam firing and the curve. This curvature that you're seeing here, this is important. This is actually part of what we want to see. And so this will allow us to give one of the measurements that we can. So at LIP, we are heavily involved in this. So we are working, we designed an alternative laser periscope. So that gives us an extra degree of freedom and therefore would allow us to cover more of the drift volume. We are also working on laser position, calibration of the laser position on the interface with the DAQ. Actually, we are in strong collaboration with LANO, especially the Coimbra workshop is for the production of a couple of parts for this calibration system. So we'll plan in terms of DUNE, we plan to deploy, well, 12 periscopes, all of them rather close to the APAs, and a few extra end wall periscopes to basically stay at the edge. And these in principle would like to be the ones with the additional degree of freedom. Another calibration mode, another calibration source is the pulse neutron source, as I mentioned before. And the idea here is to look at 6.1 MeV gamma cascades that come from neutron captures. And here it's also important to note that neutron captures are actually the dominant background for the low energy physics of DUNE. So this calibration actually allows us to get a twofold study. One is to look at the homogeneity of basically the detector response uniformity, and the other one is to actually characterize as well our dominant background at low energies. And so this is basically a DD generator. deuterium and produces basically a lot of neutrons that will spread over the detector. And one thing that is interesting here is that argon is actually almost transparent, has an anti-resonance at 557 keV. This means that neutrons, once they reach this energy, they can pretty much drift as far as they could go, pretty much as far as the whole a large part of the detector. So this is important, and this has been actually a topic for a separate auxiliary experiment that we have been involved as well, looking precisely try to confirm the existence of this this resonance. And that was the ARTIE experiment that, well, as you can see, Sofia Andrinka has been involved. And the idea is to look precisely for this anti-resonance in liquid argon. And so they use the beam at Los Alamos, and basically they look, try to validate and confirm whether this one, it allows us to basically validate the need for this neutron source and to confirm that this deep does exist, and therefore we can actually use a neutron calibration source to study. And they performed the analysis still ongoing, but they managed to look at neutron argon cross-section to measure it within 5% uncertainty, and they measured to see actually that the interaction length at 57 keV would be on the order of 12 meters, which basically reaches, well, the sensitivity that they could do. So the results, the analysis is still being optimized, but so far the pulse neutron source seems to be useful. So, of course, all of this is important, but we cannot put everything right on the end of DUNE when it is ready. And so for that, DUNE has been gone through several stages of prototyping. We started with the 35-ton at Fermilab. In the meantime, there have been other prototypes and other experiments that have similar technology. The latest generation of prototypes are the ProtoDUNEs at CERN. These are large-scale cryostats, and they are sufficiently large-scale that we can test the feasibility of the technology. So they allow us. There's a twofold objective on these prototypes. One is to check, to do the engineering tests for the construction of the detector, and the other is to actually show that our technology can work as we expect it to for DUNE. So the ProtoDUNEs, these are basically, I have here, so they have basically 7 by 7, so they are they have about 700 tons of total liquid argon mass. So these are already bigger than the first liquid argon TPC that was Icarus, that had 600 tons. So we already run it. Both of there were two of these prototypes. There was a single phase and a dual phase one. The dual phase technology is now no longer considered for DUNE. It has been replaced by the vertical drift. So single phase, but with vertical drift. These have been, we already had these go through a first run that was completed in 2019, and we are now planning to go for a second run in 2022. And so these are, both of them were installed at CERN at the Prevsan site. They both had 2 beam extensions for each of them. And these are pretty much, these beam extensions, and you can see here the pictures of, this is the dual phase cryostat, this is the single phase. This was still during construction. There's still quite a lot of stuff being built here. Now they are, well, they are being actually open up again. But the idea is that these are full-scale prototypes. We use the same voltage, drift distances that we were planning to use on DUNE single phase. As I mentioned, they are both an engineering and a physics test, because it allows us to test the installation, and there is quite an engineering challenge to install 6-meter tall anode plane wires that are extremely sensitive and extremely fragile. We are talking about 0.5 millimeter pitch wires and gigantic ton scale planes that we have to basically make move and install inside a cryostat. And of course, there is a physics goal here on these prototypes, that is to look at the final state. So the way that these prototypes worked is that we use the proton beam, and we use different targets. And from the different targets, so we could produce different kinds of particles. We would produce electrons, kaons, pions, and protons. We have protons as well. And those particles basically represent the final states of the neutrino interactions in the fire detector. So we were not looking for neutrino interactions themselves, but we were looking for the particles that compose the final states of the neutrino interactions. And so the phase one, as I mentioned, the run one already finished. So we took the first beam in 2018, and then we kept going with cosmics and to do some additional tests. We took about 4 million triggers from pions, protons, kaons, electrons, ranging from 0.3 to 7 GeV. We ran stably at 180 kilovolts as we intended to. We got a very large electron lifetime. So we got about 80 milliseconds, while the design was for 3. And we basically got a signal to noise ratio of almost 40, depending whether we consider before or after filtering the data. And we, along with that, we also got a very large sample of cosmic stopping muons. And this is basically a picture of the detector. Once it was installed, we can see the field cage, the plane, the anode plane, the cathode plane, and basically this is one full drift volume within ProtoDUNE. And considering the quality of the figure, it almost looks that there was argon in it here. So this is two events that we see. We saw, for example, this is one candidate of a 1 GeV stopping proton candidate, and this is actually a 6 GeV kaon candidate. And these are very important, and there's lots of interest to looking for the kaon candidates, because this allows us to really improve on our sensitivity for and the studies for nucleon decay surges. So along with that, there's also some analysis being done on this context at LIP, and this I'm showing actually the work from Fernando Barão, where he was actually doing an analysis of the purity. And as I mentioned, we got a purity of within the scale of 8 milliseconds. And you should consider that the design was for 3. So we really managed to prove that we can get very clean argon. And that's good, because that means that we really have a full drift volume sensitivity. And so some more results from the single phase. We can see here, for example, the DEDX distributions. You can see both the Monte Carlo and the data, and you can see that we managed to tune and confirm the data and the Monte Carlo for the different event topologies. We've made basically we managed to confirm that our models are accurate. We could see that we can separate quite well protons and muons. All of this is quite important for the physics that we want to do. And therefore, that's basically major goals and major achievements of ProtoDUNE. One thing that we also managed to do, and this is also work that has had some involved of LIP, is that there was already been one calibration run done even on the first run of ProtoDUNE. So the pulse neutron source was actually tested there. So there was only 10 days of data taking, and it was just a proof of principle to show, but there was already an excess. It was indeed observed. So you can see here that we can, with the DD generator, there is actually an excess of data, which basically means we can see the neutrons. Of course, these are preliminary findings. The analysis is still ongoing, and if you have further questions, I really recommend you talk with Sophia, that has been more involved in this. And so the summary of the first run of ProtoDUNE, we took data for about 500 days, a bit over. We showed that we could get very high quality liquid argon. We managed to show that we could operate high voltage stably with the nominal electric field. We showed for basically stability of the electrons for over a 1 year period. All these are very important objectives, and we actually got the opportunity to do some extra tests. But for example, doping the argon with xenon to get some extra scintillation, the neutron generator. And right now, our work, the detector, has been decommissioned. We are disassembling the parts, and we are going to basically introduce new technology to test. That is what we intend to use for the first module in DUNE. In particular, the new DAQ that is going to be the same as used for DUNE, using already an online software trigger, unlike the hardware one that we used in the first run. The latest charge readout and photon detection designs, and also the calibration systems that we are basically involved into. So the timeline for both DUNE and ProtoDUNE, originally we were expecting to run ProtoDUNE in 2021. Nowadays, well, due to the present situation, our schedule was pushed over. We are now aiming to run by summer of 2022. And then in 2024, we should have the installation of the first DUNE module. 2025, we should be installing the second module. And once we have a module installed, we start the physics with atmospheric neutrinos. Then 2026, we would have, in principle, the beam would be operational at 1.2 megawatts. This does not mean that we start immediately beam physics data. There's going to be commissioning for sure, but we do have, we can already collect usable data. And then 27, 29, the third and fourth module, and 32 is the long-term timeline for an upgrade for the 2.4 megawatt beam. And so this brings me to my summary. So DUNE is a long baseline experiment where we use a broadband beam, and that will allow us to make precise and simultaneous measurements of the mass ordering CP violation and the measurement of neutrino mixing angles. This is a technology that has been used before, but not quite at the same scale. And so we intend to push it to the limit to get a good sensitivity, not only for long baseline physics, but also for supernova, proton decay. We had run already prototypes, extremely successful runs. We are now preparing for a second run of ProtoDUNE to start next year. And well, this is an experiment where we are heavily involved at LIP, and we are all actually very keen on looking to DUNE to start by 2024. And that's pretty much all. Thank you.
Thank you, Nuno, for this very interesting and comprehensive presentation about DUNE. We have now some time for questions. Please raise your hand or just speak up. Please, Margarida.
É o Gustavo.
Okay. Viva.
I want to make a comment. As you know, the first neutrino oscillation was discovered in a laboratory that was in a detector that was built to actually discover proton decay. So right. I was very impressed, you know, by the limit that you quote for proton decay, 10 to 34. You know, in the beginning, as you know, the proton decay, the motivation was SU5. And there were granularification models, and there were workshops on granularification. And there were some famous experimentalists that said at the time that it was impossible ever to put a limit above 10 to 32. Now I'm hearing 10 to 34. That's absolutely incredible. I knew that this was happening. My question is, my comment is that maybe now we'll have the reverse event, that you are looking for neutrino oscillations and detailed CP violation and so on, and that the most important thing could be the proton decay discovery, because that will have a tremendous impact in our field. I would like to know if you realize that, that this experiment may do the opposite, discover proton decay and make it even more important than whatever discovery of CP violation, although that is very important in neutrino oscillations. It's a very fascinating.
I realize, and that's it's by no means a random coincidence that ultimately the final states, the reason why it was pushed, one of the targets of ProtoDUNE, as I mentioned, we use a proton beam from the SPS at CERN, but we had 3 different targets: a tungsten, a copper, and an iron one. And one of those targets was aimed specifically that we would get kaons. And the only reason for us to get kaons is because the kaon channel is very important for DUNE, precisely for the nucleon decay. So it's something, and the amount actually of the ProtoDUNE analysis going on right now, the most active ones are the study of identifying nucleon decay events, the different channels to look for the topologies and be able to really tag events that are nucleon decay candidates.
Yes, but you put bounds on in all sorts of decays, even
yeah. So kaon decays are interesting because they are unique for DUNE.
Yeah,
they are because
when will these limits be obtainable? 10 to 34 or 10 to 33?
That would imply pretty much the whole data taking. So 15 years. That would be. Yes, those require. So they require a large exposure. So usually those limits are established for the full data taking of the experiment. I mean, I'm pretty sure we will publish systematically almost every year or so that we add, because still DUNE accumulates quite a lot of exposure. It's a big detector. So once the detector is fully built, it's 40,000 tons of argon. So, and there are even studies that we could expand the fiducial volume for the nucleon decay modes, for certain nucleon decay modes. So this means instead of 40,000, we could go a bit further. And of course, after 1 year of data taking or 2 years, we will accumulate. Once we have enough statistics, we'll publish results for that. Because so 10 to the 34 is what we ultimately be able to achieve. But for sure, and I mean, we are setting a whole new range, a whole new order of magnitude on sensitivity. So we'll do interim results.
Okay.
You also said it was 15 years for CP violation.
So that is for covering 75% of the phase space. If we discover CP violation in some specific location, for example, so there is already some indication that there might be CP violation from the T2K experiment. And if there is, and it is there, DUNE can do it in a much less time. Can see it with high sensitivity, with 5 sigma within 5 years or so. So the sensitivity, the 15 years is to cover 75%. And well, as you know, where the phase, so the phase space, let me maybe try to share another slide that I have here, because the reason for those 75% is basically, so this is an outdated slide, but the reason for the 75% is because you have these regions that go to zero. So covering 75% basically means just leaving really the vicinity around pi and 0. So for right now, the best fit of T2K is something closer to -pi/2, I believe. And that makes DUNE much more sensitive and therefore requiring much faster data taking.
Very well, thank you very much. So more questions to Nuno? If not, I have one. So this is a very ambitious project, which means that it should be highly costly. How much does it cost overall? So the accelerator and the detectors. Do you have an idea, just the number?
Billions. It's on the billion. It's on the billion scale.
So it's on the LHC scale, basically, is that?
I think it's not quite that size, but close enough. I thought it was 1-point-something billion comes to mind, but it's difficult to actually put a number because US and Europe name the costs differently. No, it is important because that's the way manpower is treated. In Europe, manpower is included. In the US, it's not.
Okay.
And so costs differ. It's hard to make an immediate parallel, but I don't know if Jose is around and he knows a number, but I thought it was
more on the order of three.
Yeah. Well, okay. So it's
but yeah, I mean, or without
what?
Three with the manpower or without the manpower? Just to make sure that.
Yeah, that's the question. I'm not sure
Okay.
which. If the number came from the US, it's without.
Okay. Very well.
So it's instrumentation. It's a whole new scale. So, and it includes, and it's important to note, it includes the accelerator, which is not DUNE. The accelerator is PIP2, which is the facility. That's the long baseline neutrino facility.
Yeah.
And that's a whole different beast, so to say.
Okay, more questions? Elena, please.
Okay, Nuno, I enjoyed a lot your seminar. I have a question that regards the nature of neutrinos, either being Majorana or Dirac. So I believe that DUNE is not suitable to investigate this nature.
No.
Because the phase space goes up to few GeV, right? You need more.
Mm-hmm.
Is that
so?
That
yeah, DUNE is not. So to look for, well, to look for Majorana neutrinos right now, it's the only practical way is looking for neutrinoless double beta decay. So if you want to look for the Majorana nature of neutrinos, that is really right now the only practical way to look for it.
Oh, okay. Yeah. Yeah.
And so that's no plus.
Yes. Okay.
So that's so DUNE gives us one piece of the puzzle, and the neutrinos double beta decay experiments gives us the other piece of the puzzle. And when you combine both, you could, depending on the results that you get, you could actually start doing experimental leptogenesis.
Okay, I think it would be a longer discussion, not suitable for now.
Oh,
but
yes.
Maybe when we come back all together at LEAP, I would like to explore better this. Thank you.
Sure, definitely. So we are already 20 minutes past the hour of the seminar.
I apologize.
So no. So the questions are very interesting, but Nuno is around. Nuno is at LEAP. So if you have any more questions to him, be sure to contact him. Thank you all for being here. Thanks, Nuno, for this very interesting seminar once again, and see you for the next LEAP seminar. Bye.